Hi and welcome to another episode of the physics simulation series. Today in this video, we'll see one of the applications of a spring simulation. As promised, we'll be exploring how springs can be used to create realistic cloth behavior. But before we get into the details, let's take a look at the project demo. As you can see, the cloth moves and swings naturally. If we take a closer look, you'll notice that the cloth is made of interconnected line segments, each representing a spring. Just like the springs we discussed in our previous projects, this cloth simulation is built upon the same spring principles, including the math and the implementations we covered in our previous videos. The top edge of the cloth is fixed in place, acting as if it's hanging from certain points, while the rest of the cloth is free to move and react to forces. Now let's see some of the interactive features. The first off, we have a wind effect. If I left click on the screen, you can see a force is applied, making the cloth ripple and sway like it's caught in a breeze. With a right click, we can actually remove the springs that hold the cloth together. The cloth starts to tear apart as the connections break. If I separate a piece of the cloth entirely from the fixed points at the top, they will be removed because this piece is no longer connected to anything anchored. Our simulations automatically removes it. This keeps things clean and realistic. No more random floating bits of cloth. If you're interested in checking out the source code, I've uploaded it to GitHub. You'll find the link in the description below, so be sure to check it out. Before we wrap up, let me quickly walk you through the source code. I apologize in advance, it is not fully organized yet since this is just the first version, but I hope it will still be helpful. First, we generate a grid of points representing the cloth nodes. The grid dimensions are defined by grid size, creating a square grid. Each point's positions is calculated by multiplying its grid indices by spring length, spacing the points evenly. We then update the entire grid to position it correctly within the window. Now determine which points are fixed. The points in the top row are fixed under specific conditions. Every fifth point, the last point in the row, are all anchored. We connect the points with the springs, which provide the tension that simulates the cloth behavior. We iterate through each point, connecting it to its immediate horizontal and vertical neighbors. For each point, we take for a left neighbor and create a spring if-on to it, adding it to our springs list. We do the same for upper neighbors, creating vertical springs. While creating these springs, we also increment a counter on each point, tracking the number of springs connected to it. This grid of interconnected points on springs form the basis of our cloth simulation, enabling it to deform and react to forces later in the process. Let's see its implementation in code. As we have discussed, this code creates all the points forming the cloth structure, and these lines then establish the connections between these points by creating springs between edges and neighbors, just as we explained. Now let's explore some interactive features. Remember the wind effect we saw in the demo? It is handled by the wind effect function, which allows us to create interactive wind for our cloth, essentially turning the mouse into the virtual fan. The function checks if any point on the cloth is near the mouse cursor. It calculates the distance between its point and the mouse. If a point is within a certain range, it's pushed slightly away from the mouse position. This push creates ripples and waves in the cloth as you move the mouse, making the cloth react dynamically to interactions. In short, wind effect uses the mouse to simulate wind. Now let's move to its implementation. If the distance between a point and the mouse click position is less than 100, we apply disturbance by slightly altering its position. Now let's see how we can remove a spring from our cloth structure with the right click. When you right click, we check every spring in the cloth. We determine if either end of the spring is close to the mouse click. If a spring is close enough, it's removed. Because we have removed the spring, we also need to update the points that were connected to it. We reduce the count of the springs connected to each of those points, reflecting the change in its cloth structure. By removing springs where you click, you weaken the cloth locally, allowing for interactive tearing and deformation. Now let's look at the implementation. On the right click, we iterate through all the springs, checking if they are close to the click location. If a spring's in points is within a certain distance, say 15, we remove that spring. We also then decrement the spring connections count for the 2 points that were originally connected by the removed spring. When we remove all the springs connected to the points, or in other words, there is a point which is not connected to any spring, this helps us to cleanse off orphaned points that are no longer connected to anything, preventing memory wastage and unnecessary calculations. Now let's see its implementation in code. The function works by iterating through a collection of points and taking 2 main conditions. The first condition is the point is not fixed, meaning it's free to move, and the second condition is the point has no springs attached, indicating it has no connections to other points. If both conditions are true, the point is deleted and marking it for removal. We also need to make sure that any parts of the cloth that become completely detached from the fixed points are removed from the simulation. For instance, if the cloth is torn and it is connected pieces should be discarded to keep the simulations accurate and efficient. Essentially, we need to identify any points that are no longer connected to the fixed points by any path. So how do we find these disconnected components? We use a breadth-first search algorithm. VFS starts at the fixed points and explores all the points connected to them. Because of the breaks in the cloth from the removed springs, VFS won't be able to reach every point. We keep track of which points VFS does visit. Any point that VFS doesn't visit are by definition disconnected and can be removed. Now let's look at its implementation. First, we check if there are any points at all. If the cloth is empty, there is nothing to do, so we just return. We use a breadth-first search or VFS to find all the points that are still connected to the fixed points. Think of it like exploring a maze. We start at all the fixed points, these are our starting points in the maze, and then we explore outwards. Following the connections between the points, we keep track of which points we have already visited so we don't go in circles. The BFS uses a queue. We start by adding all the fixed points to the queue. Then we take a point from the queue, look at all the springs connected to it, add any unvisited points at the other end of those springs to the queue. We keep doing this until the queue is empty, meaning we have explored as far as we can go from the fixed point. After the VFS, we have a list of all the points that are connected. We then go through all the points again, look for any that are not in that list and that are also not fixed. These are the disconnected points that we need to remove. We store these points in points to remove. If there are no points to remove, we return. Otherwise, we find all the springs connected to those points, storing them in springs to remove. Before we actually delete anything, it's really important to update the connection count for the points that are connected to the springs we're about to remove. This ensures that our points connection counts stay accurate. Finally, we remove the springs and the points from our main list. Then we delete them to free up the memory they are using. This cleans off the disconnected parts of the cloth, keeping our simulation running smoothly and efficiently. We have already covered the physics in detail, so we can skip that part. Of course, there are other functions handling things like updating point positions with update points, calculate spring forces with calculate force, keeping everything on screen with apply constraints. That wraps up our code walkthrough. I hope this summarizes the code well. Thank you for being with me till the end. Please consider subscribing for more projects. I will see you in the next video.